All right, welcome back, everyone. Today, we're going to dive into something that's absolutely huge for GCSE physics, AQA's required practical number one. We're going to crack the code on a property that explains so much about the world around us, and that is specific heat capacity. So let's kick things off with a bit of a mystery. Picture this. You're in the park on a chilly day. You go to sit on a metal bench, and whoa, it feels absolutely freezing. But then you hop over to a wooden one, and it feels way warmer. Here's the kicker. If you took a thermometer out, you'd find they are the exact same temperature. So, what on earth is going on here? That's the secret we're gonna unlock. Well, the secret ingredient, the key to solving our whole park bench puzzle, is a physical property called, you guessed it, specific heat capacity. Every single material has one, and it basically dictates how that material deals with heat energy. Okay, so what is it officially? Let's look at the AQA definition, because you've got to know it. Specific heat capacity, which we use a little c for, is the amount of energy you need to raise the temperature of 1 kilogram of a substance by just 1 degree Celsius. Simple as that. You know, the best way to think about this is with an analogy. Imagine materials with a low specific heat capacity, like the metal on that bench, are like little cups. It doesn't take much energy to fill them up, so they heat up really fast. But they also empty out just as fast, meaning they cool down quickly. Now, things with a high specific heat capacity, like water, are like giant buckets. You have to pour in tons and tons of energy to raise their temperature even a little bit. But they hold on to that energy for ages. And that's why the metal bench feels so cold. It's not actually colder. It just has a low specific heat capacity, so it yanks the heat away from your body super, super fast. Okay, so that's the theory. But how do scientists, or you in a lab, actually measure this property? Well, that brings us to our mission for today, the AQA Required Practical 1. This is the official way we figure out a material's specific heat capacity. At its heart, the objective is really straightforward. We're running a proper scientific investigation to find the value of C for a certain material, usually a block of aluminum or copper. We're basically trying to measure its heat-storing superpower. Right, so for any good scientific mission, you need a blueprint, a plan. And in physics, that's almost always an equation. This is the secret code that lets us turn the numbers we measure in the lab into the answer we're actually looking for. And here it is, the big one. This will be on your AQA physics equation sheet, so you don't need to memorize it, but you absolutely have to understand what each bit means. It's change in thermal energy equals mass times specific heat capacity times the change in temperature. Let's decode it. See, this equation tells a whole story. It all starts with delta E, which is just a fancy way of saying change in thermal energy. In this experiment, this is the energy we're going to pump into our material using an electric heater, and we measure it in joules. And where are we putting that energy? We're putting it into M, which stands for mass. That's just how much stuff we're heating. And a classic exam tip here, guys. Make sure it's in kilograms. They love to give it to you in grams to try and catch you out. And then we get to C, the whole reason we're here. This is the star of the show, our unknown value. It's the specific heat capacity of the material, and it's the number that links the energy we put in to the temperature rise we get out. And the result of all that energy input is delta theta, the change in temperature. We measure the temperature at the start, we heat the block up, we measure the temperature at the end, and the difference is delta theta. So you put energy in to a certain mass of a substance, and you get a temperature change out. That's the story of the equation. Okay, so you know the method, you know the equation. Job done, right? Well, not quite. To get the top marks, the examiners want to see your working scientifically skills. This is less about what you know and much more about how you think like a scientist. These are the skills straight out of the AQA spec that they're looking for. Can you tell your independent from your dependent variable? Can you look at a method and say whether it's actually a fair test? And, crucially, can you spot what might go wrong, the errors, and suggest how to fix them? Nailing this stuff is the key to those higher level marks. A huge part of this is getting your head around errors. So what's the difference? Well, a random error is, when you're trying to read the thermometer and maybe your eye line is a little different each time. You can tackle that by taking a few readings and finding the average. But a systematic error? Ooh, that's a different beast. That's when your equipment is just plain wrong, like a thermometer that always reads 2 degrees too hot. Doing it again and again won't fix that. You have to sort out your kit or your method. Okay, endgame time. Let's put all of this together and talk about how you're going to absolutely nail the exam questions on this practical. Seriously, this slide is your secret weapon. The examiners are going to ask you to do three main things. First up, they'll ask you to calculate C. You'll need to rearrange that equation. C equals delta E divided by M times delta theta. And please, please show you're working. Second, they'll ask you to describe the method. Just clear logical steps. And third, and this is where the big marks live, is to evaluate the method. That means talking about those errors we just mentioned. And if there's one thing you remember for an evaluation question, make it this. The single biggest problem, the biggest source of inaccuracy in this whole experiment is heat escaping to the surroundings. Not all the energy from your heater actually goes into the block. This makes the energy you measured, your delta E, seem bigger than it should be, which in turn makes your final calculation for C too high. So what's the solution? The classic grade A answer is to insulate the block. Wrap it in a lagging jacket to stop that precious heat from escaping. So after all that, why should you care? Why does any of this matter outside the exam hall? Well, let's end with a huge question. Water has a ridiculously high specific heat capacity. How does that one fact help regulate the Earth's climate? Think about it. Our massive oceans are like those giant buckets from our analogy. They can soak up insane amounts of energy from the sun without their temperature shooting up. Then they release that heat really slowly, which stops our planet from having wild temperature swings. Honestly, without water's high specific heat capacity, life on Earth as we know it probably wouldn't exist. How cool is that?